no choice. So just to see, it is a 4-bit subtractor using 2's complement. I showed it just as an example. You can just do subtractor using 1's complement. You can do subtract using half subtractor, full subtractor. You can do by subtraction. You can just go on building up like this. You can build up any circuit for any type of algebra as big as you want. You have to just only put half adder, full adder, XOR gate, OR gate all over the place and just to play with them. You get whatever algebra you want, you get. By way of an example, I have taken multiplication of two 4-bit numbers. Just one circuit I have taken just by way of example to show the versatility of whatever we have gone through yesterday. Just to get going with that, I have shown how we multiply two 4-bit numbers. I am just taking you back to the first class where you learned numbers multiplication using decimal digits. I have done the corresponding thing with binary numbers. Two 4-bit binary numbers. The numbers are A3, A2, A1, A0, B3, B2, B1, B0. Both are 4-bit numbers. This is a multiplicand. This is a multiplier. If you just ask me casually, which is a multiplicand, which is a multiplier, I won't know because I just revised. I know this, what is put on this side is a multiplier. I don't know whether you are any better. Anyway, coming back, the procedure is take this number, multiply by the lowest bit of the multiplier, form one partial product. Is okay? Then take the next bit, that is B1, multiply by this number, form the next partial product. Do with B2, do with B3, shift the partial products, align them in proper places and add. That's okay? I'm just revising what we have gone through maybe 30 years back. It's okay? After you do the final addition of all the partial products which are properly aligned, you get the final product. Now, since it is a multiplication with base, you don't have to do multiplier, you don't have to do multiplication at all. See here, I just shown as a table A0, A1, A2, A3, that's a multiplicand. I multiplied by the least significant bit of the multiplier, B0. Next with B1, I have done the summation, that's the first partial sum. I align the next partial product, I form the next partial sum. The fourth partial product, I have got the fourth and the final partial sum. You can see here, I started off from here, so the lowest product bit will be here. As I go on adding up, the highest product bit will be here. Okay? Now since all are only ones and zeros, you will have only ones and zeros here. That is the final multiplier. You can just it looks a maze, but it's not very difficult to make out. See, all that I have done is taken A0, let's say an exact correspondence between what I have shown here and the table earlier. Here I got A0, A1, A2, A3. I have taken B0, I just put an AND gate. That's all what I have to do. For multiplication, I just put an AND gate. So, whatever the first set of 4 AND gates, whatever outputs they give, that will be the first partial product. Then, I have taken B1, I have again multiplied by A0, A1, A2, A3. They have taken the next partial product, I have aligned it properly. Is it okay? After aligning, I have done the addition. The previous one with the first one goes as it is as S0. Then this partial product, that first bit, second bit from above, and the first bit here, I put a half adder, full adder, half adder, full adder. Just to go on putting, you can get the full final product. Is okay? Alright? Just simple. That earlier table, just realize by using half adders, full adders. You can just go on expanding. In today's, see, typically a circuit like this, it requires about 50 basic electronic circuit, like if I take a NAND gate, that's a universal gate. If I take a 2-input NAND gate, it's a universal gate. About 50 to 60 NAND gates together, if you just properly connect, you can realize a multiplier like this. About 50 NAND gates. I have not calculated exactly. That's the order. 50 to 60 NAND gates will be enough to make a multiplier like this. If you take the days when 88 processor, which is the processor used in the first PC, IBM PC, if you take those days, a typical IC had about 100,000 NAND gates. So that time they found that with that processor, they cannot accommodate a multiplier. They cannot accommodate a good multiplier. So what they did, they put a separate IC, which is called the maybe multiplier unit. That's an 80, 89, and the two are combined to form the final computer. Roughly, it's not exactly complete, but your multiplication is a very big operation which you want to do every time, as small a time as possible. In today's condition, that is from 88 days to today, it is about 25 years. In today's condition, an IC can accommodate something like 10 raised to 7 universal gates. We can easily realize a 32-bit multiplier. In one IC, we can put 132 multipliers all over the place. We can accommodate it. The way it is, today's IC, whatever you want, you can put an elephant inside. It is as big as that. So whatever you want to compute, calculate, all those things you can be accommodated within the IC. The task of the IC designer has become very embarrassing. He can do so many things, but he doesn't know what he has to put inside. Everything can be put inside. IC size has become so big. So it is possible for us to go on expanding like this 4-bit multiplier. We can just go on expanding in this direction, make it 8-bit, 16-bit, 160-bit, 1600 bits multiplier. You should have more space, you have the patience to do this. This half adder, I have done the two together, I have not shown the carry. That's what you are saying, right? S5 is a mistake, am I right? S5 is 0. S5 should be 0. Even if I have 1, 1, 1, all over the place 1, 1, 1, I will have, let me try, I will not believe you. See, since you find out a mistake, I should not easily agree with you. You're right. So this S5 will be 0. This S5 will be 0. Am I right? If this is 0, here I will have only. Here, I am sorry. Okay, this here there will be an S5. I will correct this. I have to take the carry from here, am I right? Okay. Yeah. Now, just to recapitulate, a nibble multiplier, I have shown the nibble multiplier earlier. I have shown it as being built using half adders and full adders, etc. But you need not do it in such an elaborate fashion. Yeah, a nibble multiplier, you can look at it as a multiple input, multiple output, Boolean function. I got altogether 8 bits as inputs. I have to generate 7 bits as outputs. I have to generate 7 bits as outputs. 7 bits, am I right? 8 bits. I have to generate 8 bits as output. So 8 bit and 8 bit input, 8 bit output, multiple input, multiple output function. What you can do is, you can prepare the full table of input-output relationships and using logic gates, 2-level logic gates as we discussed yesterday, you can make an elaborate circuit and realize it. If you do that, it will be a well-optimized circuit. So many gates will not be coming into picture, so much of delay will not come into picture. So for example, if I this circuit, here, if I take an A0 changing, if I take A0 changes from 0 to 1 or 1 to 0, it has to propagate through, see here, all these changes it has to propagate through, etc., etc. And finally, it has to appear as a change in S7. So with all that propagation delay, it will cause a lot of time delay for multiplication, especially as the number of bits increases, the delay will increase substantially. Whereas if you put it as a multiple input, multiple output function and do the complete table in advance and realize it as a very big single circuit, it is possible to reduce the delay. Now we can expand this and make much bigger multipliers. Now when you want to do multiplication with very big numbers, broadly you have got a choice between two approaches. In one approach, suppose I take a 16-bit by 16-bit multiplier. In one approach, I can just directly extend the circuit discussed earlier. I can directly proceed with that. I can just expand it in this direction, put all the 16 bits, form all the 16 partial products, do the half adder, full adder chain and complete. At one go, I will do a multiplication. Possibly, ideally, it will give multiplication with the shortest delay. If you do it properly, it will give multiplication with the shortest delay. But it will occupy a lot of space. It's called silicon area. It will occupy a lot of space within the circuit. The silicon area that it consumes is high. Sometimes if the size of the byte, size of the number increases, you may find that it may not be all that economic, because you may do multiplication once in a way. You have to do many other things. Multiplication will be a small time operation. In that case, it may not be worth that effort. In such a case, you just use the same multiplier repeatedly. Take a byte, take the other byte, do the partial product, store it somewhere. Again, take 2 bytes, store it somewhere. You just go on doing it and then do a repeated addition. Sequentially you carry out partial product, summation, partial product, summation. That will call for additional time. Time-wise, it will take more time, but less area. In the other case, you get maximum time and minimum area. Essentially, it is a case of hardware-software trade-off. It is hardware-software trade-off at the lowest level. Whenever you do any program or any activity with the computer, you always think of a hardware-software trade-off. This is a hardware-software trade-off at the lowest level. Hardware, maximum hardware in use, you get smallest time. In the other case, you go minimal hardware, but you have to do some activity in software. That will take more time. Now, what we have gone through so far, they are all circuits for doing algebra. We have done circuits for doing algebra. These are circuits there are other types of circuits which are used for decoding and encoding. I have shown here the truth table for a 2-bit to 4-bit decoder. A function of a decoder, in the simplest terms, it is something like this. I have got I take a 2-bit number, A0, A1, the possible values are 0, 0, 1, 0, 0, 1, 1, 1. There are 4 possible values for this 2-bit number. Now, when I say decoder, this number combination will be given to a circuit which will give 4 outputs. One output will be, that output will go high when it takes 0, 0 value. Let me call this as a D0. I will have another output D1, it will go high, then takes this value. Another output D2, it will go high, then takes this value. The fourth output D3, when it goes to this value. Yesterday, we have taken some circuits of decoders where we use for multiplexer and demultiplexer. We have put it as part of the mux and demux. It's okay, that's why we have done this. I just for completeness, I am taking this separately. Just as we do with mux and demux, when suppose I want to multiplex a signal, set of 4 signals, I want to multiplex a set of 4 signals into one line, I use 4 switches. I use 4 switches and put it like this. I operate this switch by D0, this by D1, this I operate by D0, this by D1, this by D2, this by D3. So when D0 is on, this switch will be connected. I have done multiplexing of these 4 into this output line. When I do D1, when I turn on D1, this signal will be connected here, and so on. This we have done yesterday. So in this 4-to-1 match, this 2-to-4 decoder was built in. Similarly, 1-to-4 D-match. If I have 1-to-4 D-match, which we went through yesterday, you can see in the notes. We had D0 to D3 decoder lines were built in. These are typical applications of decoders. I have shown here a 2-to-4 decoder. That's the truth table for a 2-to-4 decoder. When I say truth table, what I mean is, when see here A0, A1 both are 1, both are 0, then output 0 will be 1, all others are 0. Here output 1 will be 1, all others are 0, and so on. This is a typical, simple 2-to-4 decoder. You can have different types of decoders like this. I'll show you a few examples here. So one set of applications of logic gates is in multiplexer and demultiplexer. Another major application is in algebra. The third application is in encoders and decoders. This is possibly the simplest of the decoder, directly from 2-bit to 4-bit, one of the simplest of the decoders. I have shown the circuit of the decoder here, which was earlier part of the mux and demux. 2-to-4 decoder. It's okay? I can extend that and make a 3-to-8 decoder. 3 bits to 8 bits output. When all the 3 are 0, 0, 0, O0 will be 1, all the 3 are 1, 1, 1, O7 will be 1, and so on. I can just go on extending this. There is what is called a 7-segment decoder. I will come to that later on. Typically that is used for displays, very commonly used for displays. We will just discuss that at a later stage. One very commonly used decoder is what is called a BCD decoder. Decimal numbers, when I want to represent in binary form, the simplest procedure is to go for a direct conversion. Suppose I have I have a number 847. 847 I put as equal to 256 plus 128. That makes it, I'm sorry, 512 plus 256. That makes it 512, 256, 867, 768. That leaves behind how much? 847 and 768 is 9, 3, 39, 67, 79. So plus 64 plus 8 plus 4 plus 3 plus 2 plus 1. Is that right? So, hopefully that is right. That is equivalent binary number. This is one way of converting decimal number into binary and working. Same way you can convert binary to decimal and you can just work with that. As you can see, it's time consuming. It is not always attractive to do this. Same thing with circuitry. When you work with decimal numbers and binary numbers together, you can do a direct conversion always, one way or other, and work with that. No. See, this difference between you and me, I have been teaching this for years together. So I know that 512 is 2 raised to 9. 100 times I have done. 2 raised to 9 is 1 into 2 raised to 9, 1 into 2 raised to 8, 1 into 2 raised to, I'm sorry, 0 into 2 raised to, I'm sorry, I had to spend some time. It is one way of conveying to students that you are a prodigy. It will take some time. You have to teach the subject for 10 years, and 11th year you do, then they know you are a prodigy. It's okay. It's okay. An alternate representation is what is called a BCD representation. You simply take the number 847. This number is a 3-digit decimal number. You retain the identity of every digit separately, convert and just retain. What I mean is 7 you represent as a binary number 0, 1, 1, 1. 4 you retain as a binary number 0, 1, 0, 0. 8 you represent as a binary number 1, 0, 0, 0. It requires here altogether 12 bits. Here it requires 10 bits. As you go on expanding, it requires 4 bits. But always you understand that this is a special type of representation. In this representation, this whole thing does not represent a binary number. Individual ones represent binary numbers which correspond to the decimal digits. Is it alright? Is it okay? There's a separate identity for this. an identity for this, an identity for this. It is called a binary coded decimal, a BCD. It's called a binary coded decimal. Every decimal digit has a separate identity, which is the form of a binary number. It is called a binary coded decimal, a decimal number coded in binary form. One type of coding, you understand what it means. The moment I say this, you understand what it means. But that number you have to treat separately. For example, if I take a number, if I take a number 8, 4, 7 and 9, 2, 3. I want to add up the two. What I'll do will be, take this number 8, 4, 7, take that number 9, 2, 3, do a similar representation. This will be represented as 0, 0, 1, 1, that is 3. This will be represented as 0, 0, 1, 0. This will be represented as a 1, 0, 0, 1. Then you do an addition. When you do the addition here, you create a lot of confusion. I just do a binary addition here. 1 plus 1 is 0, carry 1, 1, 0, 1. I do an addition here, 0, 1, 1, 0, 1, 0, 0, 1, 0. Alright? As I maintained a separate identity, I not mixed up the three. One confusion is, I got here a 5-bit number, which I don't allow. Another is, I got a representation here which is not available. This 1010, if we take the corresponding hex form, that makes it 8 plus 2, 10. But you don't permit that. You only permit representation up to 9. 0 onwards up to 1001. Only up to 9 you do representation. Beyond that, that is not available. So in BCD representation, any number, any digit which is represented from 00 up to 1001, that is up to 9, that is accepted. Before that, it is not accepted. So you have to convert back into a BCD. It is alright? It's okay? You have to convert back into a BCD. In fact, one of the exercises is to do this BCD conversion, BCD addition and all that. Now, any decimal number, to do a BCD conversion, there is an encoder available. Okay, and so here I just shown typical numbers. I showed typical numbers. This is a decimal number, equivalent BCD. This is a decimal number, equivalent BCD. This is a circuit which will convert the 10 digits 0 to 9 into equivalent BCD. You can see that table here. B0 will be 1 under some conditions, B1 will be 1 under some conditions, and so on up to B3. B0 will be 1 if the digit is odd. B1 will be 1 if the digit is either 2, 3, 6 or 7. B2 will be 1 if the digit is anything from 4 to 7. B3 is 1 only if the digit is 8 or 9. Okay? Is alright? Now if I want to do the encoder, if you understand that, it's very simple. I0 directly, no, it's not, we need not worry about that, it's 0. I1, see here, I just taken that, just to see whether you get a proper outputs. I1, B0 is formed by combining I1 to I3, I5, I7 and I9. Similarly, this is formed by combining 2, 3, 6 and 7 and so on. Whatever the table you put earlier, this tallies with that. So you give any one of the 10 bits as inputs, any one of the 10 decimal digits as inputs you give, Any one of the 10 you give us input, you get the corresponding BCD. This is a decimal to BCD converter circuit. Alright? That is you are asking, you are indirectly asking, where can I have an application for this?
Set of members for which regional set of members, you can say one is how did I arrive at this?
Now, there are two issues. Number one, what is the logic in doing this? Right? This is okay? Representation is okay. Now the next is, how do I, if I get a digit 0, 1, 2, 3, can I get the corresponding B0, B1, B2, B3? If I pose a question like this, the question, maybe it's a hypothetical question now. I want a digit, the digit can have any value from 0 to 9. For that digit, can I get the equivalent BCD value? The equivalent BCD, if I put it in the form of a table, it will look like this. I can have the digit value 0, 1, 2, okay. Okay, I can have the value. I think it will be better, more in order if I put it the other way around. I can have the digit value as 0, whose equivalent binary number is 0, 0, 0, 0, 1, these are the 10 decimal digits. These are the equivalent binary numbers. Alright. This is one of the illustrations of the art and science of putting something in a very elaborate manner which you can understand very easily otherwise. It's okay now. Now if you ask the question, why you do this at all? Why you have to put such an elaborate circuit? What's the purpose of this? That's another question you may ask. Okay. Now, okay, I'll give an example which possibly no longer exists, but you need, but with that you get number of examples. I give one example which doesn't exist. So far, as of now, the early days of working with computers, sometime in the 50s or 60s if you take, all the work used to be with half adder, full adder, binary representation and all that, but the familiarity is only with decimal numbers. So those days there are a lot of groping around, how to do multiplication, what way to arrange, etc., etc. One method which was suggested and widely implemented was just to have all the numbers as decimal numbers. All the numbers you give only as decimal numbers, work with only decimal numbers. Your decimal multiplier, decimal adder, decimal lookup table, everything in the decimal form, in the form of digits. Because they are familiar with that, it has been going on for centuries. So we are such a, we are so possessive of that, and that was retained. So within the computer, every number was represented in the decimal form as much as possible. Where it is inevitable, you convert to binary form. At that time, the complete algebra used to be done in decimal form. The number was represented, individual digits were represented in this form. Okay? A 3-digit number used to be represented like this. When you do an addition, these two you add, you just see, do a corresponding circuit, you see whether you have got a carry, decimal carry. There is no binary carry here. You see whether you got a decimal carry, take it and carry over here. See whether you got a decimal carry over here. Like that, the Delaware circuit was worked out and everything was implemented in that manner. That was a very widely prevalent set of applications with a BCD. It was very common. Today, a BCD, binary coded representation, binary coded decimal as a representation is much more limited than those days. But even then, you come across real applications, you get this. I will just see in a few cases. I'll proceed. I can think of that. Since I was saying this offhand again, I'm just taking a cue from what you're saying. I can think of that offhand. What Mr. Kumar is finding out is, in one application is like this. Suppose I take a digital voltmeter. The simplest digital meter is a digital voltmeter. You have got a voltage which you sample. You get a value. That value will be converted into a number in an ADC. In an AD converter, the value will be converted into a number. So you have got an analog signal, xt, you take a sample. The sample will be taken at time t0, that will give you a value x at time t0. Okay, that will be a analog value. This you convert into equivalent digits, say a 10-bit digit. If you take a 10-bit digit, this should be represented as a 10-bit digit. That's a binary number. If I take a decimal number, it will be put as a 3-digit decimal number. We put as a 3-bit decimal number. So you can do a conversion and put as a 3-digit decimal number. Okay, you can do a conversion and put as a 3-bit decimal number. Now, in some cases, it may be necessary for you to do a correction. Say, for example, I got a voltage, I want to correct for ambient temperature variation. You have to add a small number to that. You just put it as a BCD. Within that, you work it with a BCD adder. Or you have got a pressure signal, you have got an equivalent voltage, you have taken a sample, you have got this, you want to display it in terms of a particular scale factor, either PSI or bar, millibar, etc., etc., whatever, kilograms per centimeter squared. Depending on the conversion factor, you have to put a corresponding BCD multiplier and work with that. I'm just giving a typical example. Something like that. I'll proceed. Now this is another encoder that you come across often. I like to, as an example, I have taken something which will be regularly you see in digital systems. So I would like you to just patiently go through and get a feel of that. Maybe you may feel that what's the relevance of this to my sitting across and listening to all this. But please go through this and get a feel. Okay, I've shown here something. Whenever you want to convey something, we build redundancy. You are listening to my English. I think many of you follow my English. When I talk, many of you follow my English. When you talk, I think I try to follow your English. The accent is different. Even though the accent is different, we try to understand this. When an Englishman speaks English, we follow reasonably well. When an American speaks English, we don't follow all that easily. It is because our English is closer to the Englishman's English, thanks to his passing over us for a few centuries. Now, we are able to follow the Englishman's English because there is a lot of redundancy built into the whole language. My Tamil and Sukumar's Tamil, there is a lot of difference. But when I talk something, he understands it is Tamil. It is because there is a redundancy built in. Same thing with every language. The redundancy that you build in your message makes the message secure. The other person can easily understand. I just have shown a few examples here. See here, I've taken a word, I've taken the word book. If I write this and give it for typing, one man may just change that O to A and make this. Another may change it to that K to L. Another may change from B to C. Another may change the K to F. It's all right. This 4-digit, the 4-digit, not 4-digit, 4-letter word. This 4-letter word with a single change, the whole thing is changed, and I think you have no way of making out that what is required to be conveyed is a book. It's okay. What I'm saying is the redundancy that is built into the word, it is not high. You please try elephant. You please try elephant. You try to change one or two letters in elephant. If I give you this as the word, you can easily make out this elephant. Any one letter you change, you can definitely say, look, I'm talking of an elephant. The word is very big. You have built in a lot of redundancy into it. Same way you take you can make out as an elephant. But suppose I take here P, Q, E, S, H, okay, R, N, A. I changed 1, 2, 3, 4, 5 of them I changed. I don't think you can come back to the elephant. Am I right? You cannot come back to the elephant. What I have done is, I have started off with some entity. I have built a substantial amount of redundancy, saying that if you change one or two letters in this total number of letters, 1, 2, 3, 4, 5, 6, 7, 8 letters, in these 8 letters, if you change 1, 2, 3 letters, the elephant is not going to change. Up to 3 possibly the elephant can put up with that and retain its identity. But if you change beyond that, the elephant says, I give up. I am no longer an elephant. It's alright? The identity is not maintained. You have built in a substantial amount of security, redundancy. If I take a word like table, see here, I put altogether 5 letters. If some letters change, you can make out this table. But if the table becomes cable, you cannot make out. If it becomes TABJLE, maybe you may be able to make out this table. So, as you increase the redundancy, the reliability increases substantially. But you have to put in a lot of effort. The elephant is a very long word. Substantial redundancy is built in. Security is built in. This is a short word. redundancy that you have built in is low. If you don't build in redundancy, the reliability is also low. Normally, in data, you have got data to be in digital systems, you have got data to be stored, data to be transmitted over a transmission line. It has to be received. It has to be handled in bulk. Or in all these activities, there is a possibility of corruption at every stage. Since there is a possibility of corruption at every stage, you try to build in redundancy. You put, instead of sending 10 bits, you send 12 bits, 15 bits. By some logic, you build a redundancy inside. The amount of additional bits that you build in, put into that, to that extent, that data becomes secure and you can retrieve your original data. This is done in all data processing work. In many of the activities that we deal with in digital systems also, it is built in. The simplest way of building such a redundancy is what is called a parity bit encoding. That is for a set of bits. For a set of bits you are transmitting, you just add one more bit and you call it a parity bit. The set of bits you transmit, you take a set of, say, typically I take a set of 8 bits, I add one more bit. It is something like a God bit, it is like a policeman. 8 bits, 9th bit. The two together makes it somewhat secure. That 9th bit that you are adding is called a parity bit. Now, adding a parity bit forms the most elementary form of building security or redundancy in a digital system or in any system. As I told you, binary number system is possibly the most elementary form of number system or logic system. Just extending that, if you build one parity bit into a set of bits, that forms the most elementary form of building redundancy or security in the system. For that, what you do is take your total data that you want to transmit, put into small segments. Possibly, the most attractive one is into bytes. But that you should decide beforehand. Say that all the bits I will take and put every set of bits into groups. The size of the group is fixed. Once you fix that, you can just build your parity. In line then, whatever we have done with these words, when we do data transmission, for every 8 bits, you add a 9th bit. For every 8 bits, you add a 9th bit. So that whatever you are transmitting is in groups of 9 bits. Data groups of 8 bits. For every group of 8 bits, you add 1 bit. That gives you groups of 9 bits. So I am transmitting, I am dividing my data into essentially groups of 9 bits. Plus, I am ensuring that in each group, the total number of ones is always odd. Number of ones is always odd. For example, I will not transmit 0, 0, I will not use this. This is bit 8, bit 7, bit 6, 5, 4, 3, 2, 1, 0. This is not transmitted. This can be transmitted. Suppose I get this. Altogether 1, 2, 3, 4, 5, 6. If This is what I'm going to, okay. I'll have a one here. If I take B0 as the parity bit, if I take bit B0 as the parity bit, here, if I get this as the bit combination to be transmitted, I will make this 1. So altogether the total number of ones is 4, 5, 6, 7. It's okay? So this is the parity bit I am adding. By doing this, I have made the data a bit redundant, a bit secure. When I do like this, I ensure that such a transmission is not taking place. A transmission like this is not taking place. This is not transmitted. This is not transmitted. I started off from this 8-bit number. I added this as a parity bit. When I transmit, I may receive like this, where there's an error here. I know it is an error because I count the number of ones here. That is E1. It's not permitted. Simply dump it. You discard. There's an error here. The error is in this bit, not in this bit. By looking at it, you don't know where the error is. But you know it is an error. You discard. So, by adding one parity bit, by a lookup, that bit combination of 9 bits, you are able to make out there's an error. If there's an error, you say that I will not look at it. You don't accept this. You don't accept this. You don't do anything beyond that. Okay? You cannot retrieve your data. By adding one parity bit, you just say that there's an error, there's foul. You blow the whistle. You are like an opposition party. I oppose. I don't take this. You don't do anything constructive. You simply dump the data. Okay? By adding one parity bit, that's what you're doing. So the implications are many. Firstly, I assume that for every 8 bits, the maximum error that can occur in the system is only 1 bit. Suppose 2 bits are in error, you are in trouble. So you should ensure that in your system, the maximum error in 8 bits together is either there's no error or maximum there is 1 error. Suppose there is more possibility of error, you reduce the total bit size and then add a parity bit. It's alright? That's 1. So you should ensure that there's a match between the error possibility and the size of bit that you are grouping. Second thing is, all that you are doing is just dumping the data. Now, in the digital system, where you are using this parity bit for building redundancy, you should have a scheme by which this can be identified. For example, in a microcontroller-based system, there will be a transmitter and a receiver. The transmitter will add a parity bit and transmit the data. The receiver will get the 9 bits and check whether there's a parity error. There's an error. After checking, it finds there's a parity error and is discarding the whole bit combination. Whenever a bit combination is discarded, that receiver microcontroller will make a noting. Look, there is an error. It will just blow the whistle once. At a higher level of the program, you should identify this whistle blowing and the whistle should be heard by the transmitter. You understand? Some way you should communicate to the transmitter, look, this bit combination that you sent, it's all foul, it's messed up. Just for what you are informing. Now you can do different things. One way of doing it is, whenever you just blow a whistle, the transmitter will just transmit everything all over again. Or you put 100 bytes. For every byte you put a parity bit, you transmit. After getting 100 bytes, the receiver will send back a byte saying that everything is fine, I have received. Or it may say that in this combination, some byte, it was messed up. Transmitter can send all the 100 bytes again. So for every 100 bytes, you can have an acknowledgement signal. The acknowledgement signal will be, look, I got received, okay. No, there's one mess up. One mess up, you do all over again. Okay? Or you can just send precisely, there is a method with the 57th byte, send only that. That makes it more precise, but it requires a higher, more overhead surgery both ends. You have to say 57, that fellow has to just go back to the table, look up the 57 and then send only that, but only you are sending only 1 byte, so you are no longer confining to 100 byte, etc., etc. These are all part of, transmission, protocol. Same thing with storage. Whenever you store data, you put to parity bit at regular intervals and you store the data. When you retrieve, you do all this checking and then see whether that's okay. Whenever in a computer, whenever you open a file or you get an internet file coming and all that, when it shows error, it is essentially starting off with a parity bit and in an elaborate manner it is showing you there is something wrong. Or everything starts off with a parity bit. Yeah. Okay, it is something like this. Again, put up with the digression a bit. About 50 minutes I'll take. If I take an unlocked system, I transmit time versus x, an unlocked value, some signal. I can, one way of transmitting is directly, or you can transmit in sample values. I can sample it at these intervals. I can sample it at regular intervals. In the sample values I send. Now, this sample value is this sample value is this, and so on. Okay. I'll send the sample value directly across a wire. I measure the value and use it as it is. This is analog transmission. But if there is some corruption, there is some noise, there is a pickup, this may be 1.578. The value here may be 1.578. Now if it goes to 1.579 or 579 or 577, there's no way of knowing whether there's a value, actual value, or it's a corruption. That's what Kumar is pointing out. There's no way of knowing. But suppose I just go one step further. I put a restriction. I will not send all these values. I will not send all these values. But the simplest way of building some redundancy is I will say that I will send only values 1, 2, 3, 4, 5, etc. Nothing, no other value in between. So if it is more than 1.5, I will send a 2. If it is more than 2, if it is more than 2.5, I will send a 3 and so on. So any value between 1.5 and 2.5, I will send away 2 only. Okay? I have started off the signal. I have done a sampling. I have done a quantization. At the beginning itself, I am saying that I am prepared to accept a certain error in my transmission. That is, I have done a rounding off. I have done a round off. I intentionally done a round off. I consciously done a round off, and I am sending only this. I have already introduced a certain amount of, consciously I have introduced a certain amount of error in rounding off. But at the other end, any value I get between 1.5 and 2.5, I interpret as 2. Any noise, corruption, pickup, any noise that is limited to 0.5, plus minus 0.5, I know that This is the value. If it exceeds 0.5, you have no way of retrieving the original data. But if you are sure that your corruption will be limited to 0.5, you have got your original data. Okay? Basically, this is the crux of it is this. The rounding off that you have done and introduced an error, what you have gained is a certain amount of fidelity, a certain amount of reliability of it in the system, whereby I know that if my noise pickup, any other pickup, disturbance adds a maximum of only 0.5 anywhere in the data, I am sure my data is right. So the confidence with which you say that I have done a proper transmission, I have stored it properly, etc., that depends on the confidence level with which you have done a decision on this. The error that will come into picture due to maybe, suppose I take temperature. I got a thermometer, which will give temperature up to 1 degree. If my environmental changes do not affect the temperature by more than 0.5 degree, I'm well off. If it exceeds that, I'm in trouble. You have no way of knowing whether it's an environmental change or that's a new value. So, in a digital system, binary system, this is just one general case, binary is a specific case. When I send a 0 or 1 as a bit, when I send a 0 or 1 as a bit, I am saying that in a circuit, I send 1 as a 5-volt signal, a 0 as a 0-volt signal. What we are proposing, yesterday, in fact, Guru was especially asking this. A 0 is sent as a 0-volt signal, a 1 as a 5-volt signal. One case I have shown. Any value if I receive more than 2.5, this I call as a threshold. Any value more than 2.5, I will take it as 1. Any value less than 2.5, I will take it as a 0. So I assume implicitly here that the error that I introduced is a maximum of 2.5 volts. It's okay? I have answered your question. So the whole system, you should find out, make an estimate of the total noise content. Okay, the noise content out of 1000 samples you take, or 10 raised to 6 samples that you take, out of 10 raised to 6 samples you take, there's a chance that in one sample it may go in error. There 1 may be 0 or 0 may be 1. If you are sure of that, correspondingly it will reflect as a level of reliability on the data. It's a threshold value. If your noise content is high, you have to correspondingly increase the threshold value. It's okay. Yeah. Yeah. You are saying that you have started off with a value 1.5. I got say 1.5001. You have transmitted this as a 2. To this, you have got a noise which is 0.5001, which will be interpreted as 3. Yes, that can happen. In the extreme case, that can happen. It can happen. Now, what are you asking? You are right. You are right. Now, the contestation level that you fix should be such that this interval of 0.5 plus minus 0.5, that error possibility should be some of this order. It should be of this order. If the error possibility is of this order starting with, you will end up with, in the worst case, you will end up with an error like this. Is all right? The error on the other side will be always, it will be twice whatever you have started up with. Actually, it is more often, it is the hypothetical, this you start off with some assumption, you make an estimate of the error possibility, and it is of this order. Now when I say it is of order of 10 raised to 6, when I say the error is of the order of 10 raised to 6, you cannot ask me, look, I have a case whether the error is 1 in 10 raised to 5. You understand? I am saying the error is of the order of 1 in 10 raised to 6. I have an instance where error is 1 in 10 raised to 5. I can have an instance, but you cannot question me by just giving an order. You are giving a specific example, which is very extreme case. You may have a case where the error is 1 in 10 raised to 4. Alright? Once one gentleman was telling me a case where a hardcore mathematician, whenever he goes by plane, he carries a bomb. He carries a bomb with him. And he tells the that security fellows, look, I am having a bomb. The chances of a passenger having a bomb in a plane is 1 in 1,000. The chance of a passenger having a bomb in the plane is 1 in 1,000. I already have a bomb. If I carry a bomb, the chance of another passenger having a bomb along with me is 1 in 10 raised to 6. So the chances of your plane being, having a bomb and having a problem is very remote. You understand? He is trying to justify this. It is something like that. So it is an order. It is just an order. We will continue. So for retrieving, you start off with 8 bits, add a parity bit. Odd parity is more common. Odd parity is more common because when you use even parity, sometimes you will find that the total number of, I cannot always say that, but when I say even parity, all or 0, 0 is one case. Now when all or 0, 0, always you are uncomfortable if you whether you have got a data or not. To avoid that, you just go for odd parity, but I am not right, there is something else. So here, the basic assumption is the error possibility is very low. Error possibility is very low. If at all in 8 bits there is a maximum of 1 error. That's, you start off with this assumption and do parity checking. The corrective action can be in terms of read, transmission of data, rejection of the whole packet. This type of rejection or decision is left to the higher layers. Even parity checking is similar to odd parity checking. Now you can build upon the logic, and instead of putting one parity bit, you can put 2, 3 parity bits and make the data more redundant. Of course, these are all dealt with in very great detail in data transmission schemes. I think we'll just leave it there. It is just like elephant. You put more and more words and make it more reliable. Now, coming back here, the process of doing parity checking is done by putting exclusive gates. You can check upon that. See here, I have done a circuit for parity checking. You just check up this and see whether you get it properly. I have done simply repeated exclusive operation and then got the output. You just see here, if B0 and B1, both are 1 or both are 0, I get a 0 here. That's a basic parity checking. Both are 0 or both are 1, I get a 0 here. If they are unlike, I get a 1 here. So by putting exclusive gates continuously, I am implementing an odd parity check. Okay? By repeated use of exclusive gate, I do an odd parity check. For an even parity check, I have to just put one more gate, that's all. Now, basically an exclusive gate is a 2-input gate. The multiple number of bits are added, XOR together, and this is a symbol used for multi-bit XOR gate. It is essentially a set of 2-input XOR gates. So parity checking is done by repeated XOR operation. So earlier we discussed the decimal to BCD encoder, we did parity encoder. Now I have taken one more encoder called a gray code encoder. A decimal number can be represented in terms of binary bits. One common way of doing it is just the binary number representation. You take a decimal number, put the equivalent binary number representation. That's a very common way of doing it. Like what I have shown here in the table. I think you please look at your notes. I think this may not be very clear here. 0 is represented as equivalent 0, 1, 2, 3, 10, like this, up to 31 I have gone. The first column is a decimal number. The second column is the equivalent binary number, blind binary conversion. That is, every position has a weightage. Bit 0 has a weightage 2 raised to 0, next bit has a weightage 2 raised to 1, and so on. That's direct decimal to binary converted number I have shown. That's one way of representing a decimal number as an equivalent binary number. There are many other ways. You can represent in thousands of ways you can represent a decimal number as an equivalent binary number. I have shown a second way of representing decimal number in binary form. This is a popular representation called gray code. This is called the gray code. The way I have shown here, you please go scan through the gray code. You scan through the gray code. One position to the next position, only one bit will change. I messed it up. 0, 1, 1, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0. Yeah, I'm sorry, yeah, it's right. 1, 2, 3, 4. It's right. It's okay. Goes like this. 1 is represented by the combination, 2 is represented like this, 3, 4, 5, this is another representation of decimal number. In this representation, you can see here, from this bit combination to this, there's only one bit that changes. At every stage, only one bit will change. From here to here, there's only one bit change. From here to here, there's only one bit change. If you take a corresponding binary number, if I take 4 to 5, if I take 4 to 5, 0, 1, 0, 0, 5 will be 0, 1, 0, 1. There's only one bit change. If I take 5 to 6, 0, 1, 0, 1, 0. If I take 6 to 7, it's a 1-bit change. If I take 7 to 8, I got here all the 4 bits are changing. Unlike this, in the gray code, only 1 bit changes. So whenever you are doing a, you are doing a conversion, say for example, if the bit combination is changing, when it changes from here to here, if you sense the change, only 1 bit is changing here. Here, suppose you are changing suppose this is changing first, then this, then this, then this. Then depending on when you are sensing, you may take it as a 7, 8 or any of the other combinations. Is it alright? Suppose you are taking a typical example will be that of a converting a position into a number. When you convert a position into a number, corresponding number, I can use a gray code or direct binary. If I use a gray code, if I just go on doing this, at any time from this, when I change here, there will be 1 bit changing. When I change from here to here, in this area, you may have, only 1 bit is in this area. First this bit may change, then this may change, then this may change. Depending on when you are sensing, there is a possibility it may be interpreted as 8 or it may be interpreted as any of the other numbers. Suppose it is changing from 0, 1, 1, 0, and then it goes to 0, 1, 0, 0, then it goes to 0, 0, 0, 0, then it goes to 1, 0, 0. Suppose the change sequence is like this. That is from here it is going through this, then this. During this time, if by mistake you are slightly off at the time of reading, you read any of this, it will be interpreted as either a 4 or a 0 or a 8. So you can be very much in error. This type of error will not creep up when you use a gray code. It's alright. Whenever you convert from a position, direct analog position into a corresponding number, always a gray code is preferred. In all transducers, wherever the input is directly converted to a digital number, invariably a gray code is used. So when you use a gray code, at input state, the number is available in gray code. But you would like to get it in binary form. Some cases, you have to convert from binary to gray code. In all such cases, you have to go for a encoder or a decoder. Actually, this is one logic which is commonly used. One logic that is commonly used. One way of doing it is like this. Lowest bit you make 0. 2 bits you make 1, 1. 2 bits 0, 0, 1, 1, 0, 0, 1, 1. Okay. I know this as I am telling. I am saying you shut up your mouth and follow what I am asking you to do. For the next bit, just as you made 1 bit 0, you make 2 bits 0. 4 bits 1, 4 bits 0, 4 bits. For the next one, you make 4 0, 8 ones, 8 zeros like that. Here, 8 zeros, 16 ones, 16 zeros. For the next one, okay, that's blind writing. If you go by the logic, the logic is like this. I started off with 0. I take the first bit, I make it 1. Okay? I got the next one. From this, I want only one change. Always I start off from here. I want only one change. The next one, I make this one. I retain this one. I retain this. Alright? Having done that, for the next one, I can accommodate only one change. I would like to do with minimal number of bits. I make this fellow 0. Alright? I go ahead. From this combination, I have to put one change. I have done whatever I can do with 2 bits. I have done whatever. So gray code with 2 bits will be stopping here. If you want to go beyond that, you have to go for the 3rd bit. Put the 3rd bit as 1. Now having put third bit as 1, when you go next time, you can make that 1. That's the change you do. Next time you make this 0, next time you make that 0. You have done whatever you can do with 3 bits. Then you have to go for 4th bit. You make that 1. Same logic you proceed. The moment you come here, for these combinations, that whatever you have done here, the template you have to repeat. 1 bit you have shifted, the only thing you completely repeat. It's okay. Of course, this we discussed. So it is always useful to know the conversion from binary to gray and the reverse. Now, this you can just check up whether you are getting this. You please check up, put the binary code and BCD, gray code separately. You will find that always the highest bit, the most significant bit is same for both of them. In the binary code, bit Bn, in the gray code, if I represent that bit as Gn, the highest bit is always same. For binary and gray code, this bit is the same. Other bits will change. Now the relation connecting binary and gray is the ith binary bit is equal to the I plus 1th binary bit XORed with the ith gray bit. So this gives the conversion from gray to binary. Please you can check up that table. This gives a conversion from gray to binary. So that's the circuit. You got the gray code, you got the binary. Gn is same as Bn. Bn minus 1. I take this and just work. You can just continue like this. That gives the gray to binary encoder. The reverse. Binary to gray. This form the relationship. Again the highest bit is the same. The other bits are given by these relationships. That gives the corresponding encoder. You can verify this later on and see whether that is okay. Both of them use the same number of bits. An n-bit binary, when you convert you get an n-bit gray code and vice versa. Now, yesterday, last, one of the hours and today, with whatever we have gone through, we have done the basic binary logic. We have done the binary logic. That is, if I got a bit, I can complement it. That's the only operation you can do with a bit or a bit combination. Every bit you can complement. If I got two numbers A and B, or numbers or bit combinations, okay, A and B, well, I can do an OR operation. Bit by bit I can OR them. I can do an AND operation. I can do an XOR operation. I can do an NAND operation. I can do NOR operation. These are the logic operations I can do with two bit sets. One set of bits, another set of bits. All these operations I can do. I can take A, I can complement that. I can take B, I can complement that. I exhausted all possibilities. I can also treat the bit combinations as numbers. If I treat them as numbers, well, I can add them. I can subtract. I can multiply. Okay? Etc. etc. I can do. What I am saying is, with whatever you have gone through, you can do a set of operations on bit combinations. It depends on how you look at the bit combinations. If you look at the bit combinations as just logic, variables, you can do logic operation. If you look at them as numbers, you can do algebra. You can have circuit for every one of these. With whatever you have gone through, I can have a circuit for this. I can have a circuit for this. I can have a circuit for this. I can put 10 circuits. I can get all the outputs. I have here the bit combination A. I have bit combination B. I put one circuit. That will give me OR output. I put second circuit. That will give me AND output. I just put circuit after circuit after circuit. Finally it gives me subtracted output. Okay. I can tell you, I put all the circuits I want. Whatever circuits you can think of with two sets of bits. Whatever circuits you can think of, whatever operations you can think of with two sets of bits, I have put here. And I tell you, it is up to you to choose what you want. Now, I'll add something more here. I'll put a set of multiplexers. The multiplexers, I give you the option. What is the function you want? You want this function, you want this function, you want this function. I'll assign a number to this. 0, 0. Assign a number 0, 1. Assign another number. Okay. You select the number combination. I will take that output and make it available to you. Is all right? I put all the functions. I put a set of multiplexers. The select bits you use. You select the function you want. It becomes an elaborate, algebraic, logic unit. It is called the ALU. ALU is an integral part of every digital system. It is nothing but a set of logic gates strewn all over, arranged in a well-organized manner to do any operation you want. A box of functions, all the functions that you have put inside, you give your bit combinations, A and B bit combinations as inputs. You have a function selector. The function selector will have a set of bits, which is essentially a decoder. That function selector will select the outputs from individual functions that you want and give it out. So an ALU is basically a unit which accepts two sets of bits and it selects a function that you want to do and makes that available to you. Is all right? It is up to you to select your function. If you are clear what you want, you just use that output. The box has a variety of functions which are defined. You select your function through the select line, get the desired output. Now, with today's IC size, it has become possible to elaborate and to have elaborate ALUs realized. I have shown here a typical example of a single bit ALU. Don't laugh at me. All I am saying is, if you have got two bits, A and B, what all you can do with them, I have put number of them together here. Say for example, you can do an AND operation. With 2 bits, I can do an AND operation. I can do an OR operation, XOR operation. I can invert bit A, invert bit B. I can do a half adder or full adder. I can take a carry from somewhere else and do a full adder. I can do a full subtractor. I can do any one of these operations. I got a 3 to 8 decoder. With 3 bits, I select any one of these functions I want. I steer that to the output side. That single output bit is what you want. What I am saying is with only 2 inputs bits, 1 output bit, I am taking a lot of effort to tell you that you can generate 1 output bit. But the point is it has got an identity. The identity is whether it's an AND operation, OR operation, whatever operation you want, the corresponding one you have got here. This is a single bit ALU. A single bit ALU is just to scale it up, you get 8 bit, 10 bit, 16 bit ALU. It is just a direct scaled up version of this. It is an integral part of any digital system. Now, the challenge is something else. Suppose I want an operation to be selected. How do I do this? How do I say that, okay, first I give 1 set of bits, get that output, then next set of bits, get an output. I have to just store it and then use it. I have to just go on doing this. These things we have not done so far. But as of now, you want any particular operation, you identify the bit combination that is necessary for that operation, give that here, you get that output from that black box. That is an ALU. Okay. I think we should have a few minutes break. Am I right? About 5 minutes we'll have break. Hmm? For every bit, I add one more bit. For every 8 bits, I add one more bit. That's called the 9th bit, the parity bit. One way of doing it is by just counting the number of ones and deciding the parity. If the total number of ones is given, make the bit 1. If it is odd, make it 0. It is called odd parity. I think we'll stop here. We'll have tea, come back. Okay, Munya announced tea. It's okay? Now we'll take up the next topic. We are going to deal with what are called flip-flops, counters and registers. They add a completely new dimension to our working. Earlier with what we have seen, we have got binary numbers, binary algebra, on the other side you have got Boolean variables, logic functions. There's a one-to-one correspondence between the binary numbers and whatever we do as algebra and Boolean variables and the corresponding logic functions. There's a one-to-one correspondence with every one of the activities. We identified and we exploited this to a very great extent. But in whatever you have done, everything exists only at the present. The first case is that of the ALU we have seen earlier. With an ALU, I select a function, I give all my bit combinations as input, I get an output as a sum. The moment I change this, the sum is disappearing. So what I do now, I get an output now. There's no time factor, no memory, no storage, no carryover. Nothing is available as of now. The whole existence is at the vibrant present moment. No past, no future. Time dimension does not exist. That is one thing that we can identify with that. Since the time dimension does not exist, the question arises, can you bring it in? If you bring in time dimension, you are adding a completely new dimension to the whole activity. That is precisely what we are going to do now. So this is the question and this is what we are going to do. Yeah? Yeah. Sumar said I have to press S5. I refuse to do that. F5, Sumar. Okay. Basically, we won't involve time as a continuous element here. We use time as a discretized variable. Everything we are working in a discretized fashion. Same way we say that, sorry, I take the values at 0 second, 1 second, 2 second, and so on. At discrete instance of time, I just give an interpretation to whatever activity I do and work with that. That's one basic thing we start with and proceed. I have shown you an abstraction of a complete digital system. It is worth spending some time with this. A complete digital system will look something like this. I give an abstraction. We should be able to identify whatever we do as a digital system in terms of this. See here, to the system, I give a set of logic inputs. I put them as I1, I2, I3, etc. All these are logic inputs. Or a binary number, a set of logic variables, combinations of binary variables, binary numbers, logic variables. All these are inputs here. And that system is giving a set of outputs. All these outputs are either binary numbers or logic variables. Here, I got a set of combinatorial relations, AND gate, OR gate, logic gate, adder, subtractor, half adder, full adder, half full adder, whatever you want you put there. A set of logic gates are put inside. A set of combination relations, typically an ALU, something like that I got here. Now, I have added a memory element to this. What I have done here is, at present, whatever input I give here, from the combinational circuit, I generate a set of outputs that I put to what I call as a memory. These outputs I store. I store here. At the 0 time, whatever I store here is in this slice. At the previous time instant, whatever I stored was available here. That is calculated, computed, and pushed into the storage. Again, at second -2, that was stored here, and so on. All these are past layers of storage. Whatever I computed from here, by my logic combination circuit, I stored now. The previous storages are available here. Okay? Now what I do is, I take all from previous storages, I extract information. I extract information from here and give it as an additional input to the combination circuit. I extract information from here and give us additional information to the combination circuit. So I get all the present inputs, I got all the past stored values, I combine all this, I generate my outputs. I use all this, I generate the storage. It is okay? It is alright? You take my behavior. My behavior is a conditioned behavior. I respond to all the inputs I get at this instant of time. Plus, all the past things I committed, all are stored in my system. My present behavior is fully conditioned. Maybe in a negative sense, I can say corrupted and conditioned by whatever I have stored inside as processed data. If I take Arul, I feel that last year, January 10th, I got a fight with Arul. I don't like this fellow. That is stored inside. If I take Vijayalakshmi, I know she's a very charming girl. So when I behave, suppose Vijayalakshmi calls me, oh, you are an idiot. This is coming from a charming girl, so I am an idiot. Whatever stored data I kept inside, whatever present input she has given, I combined the two, I have given an output. Arul, when he says he is an idiot, look, this fellow is useless fellow, he is already conditioned in his mind, so I should not worry about what he is saying. When he says you are an idiot, actually he is an idiot. Whereas with Vijayalakshmi, she is a charming girl. My behavior is conditioned. I have taken the present inputs, I have taken all my stored values, I have done a recomputation, I have given an output. That is an abstraction of a digital system. Whatever we have dealt with so far is this portion. All present inputs, do a combinatorial relationship function, get your output. This is what you have done. Now, if we know what is storage, how you store, you have made a basis for any digital system. So we will be dealing with this portion, DSP. If I slightly extend this, analog modeling, if I take a system, modeling behavior of system, impulse response, or you take what is that? You take input and the impulse response and do that, convolution. Okay, you can build up all this, filter functions. Okay, all this you can just build based on the basic abstracted digital system. it requires a set of sequential circuits to be handled. So we should know what the sequential circuits are, the items to be stored. When we do this, it adds substantial to the capacity of the digital system and how we can work with that. Now, with that as a preliminary, I have shown the most elementary form of unit which can store data. A unit which can store data. Once again, I have used only the basic universal gates that we are familiar with. I have taken two NOR gates. I have taken two NOR gates and I have connected in a particular fashion. This is called a flip-flop. When somebody introduced this in a equivalent vacuum tube version, sometime in the 30s, it was considered very, very revolutionary development. He did something, took two items and just crisscross connected, and he said, look, I can get this. This is a highly revolutionary system. We can see what it means for us. I have taken, just I made a circuit with two inputs. I call this input R, I call this input S. I have taken the NOR gate here. I got an output, I call it Q. This output I call Q bar. I assign this Q and Q bar here. This Q bar I connected back here. This Q I connected back here. Now we can see how it behaves. If I take S as 1, if I take S as 1 and R as 0, S as 1 and R as 0, you can see Q bar is 0 and Q is 1. Okay? Is it alright? S as 1 and R as 0, Q bar is 0 and Q is 1. Same way, if I take R as 1 and S as 0, the other way around. Q is 0, Q bar is 1. This is called a set state. When Q is 1, the flip-flop is said to be in the set state. When Q is 0 and Q bar is 1, is said to be in the reset state. Okay? The first two are clear. The first two sets are clear. Behavior is very clear. Unique behavior, depending on R and S combination, that is, they are unlike, behavior is very clear. Now let me take the case when both are 0, 0. If both are 0, 0, coming back, if R is 0, as far as the NOR output is concerned, this is an OR gate. If this is 0, output is decided by this. This is also 0. This output is decided by this input. So when R is 0, before R goes to 0, if Q was 1, this should have been 1. Since this is 1, this is a 0, it will be retained as it is, the old state will be retained. Just to consider both the cases. Take the case when R was 0 and S was 1. R was 0 and S was 1. Now you take S from 1 to 0. This was 1, this was 0. Since this was 1 and this was 0, that output was 1. Since that was 1, this quantity is a 1. At that time, even if I make it 0, this output will not change. That will retain the old 0 value. Old 1 value will be retained here. Am I clear? Am I clear? Is it alright? No. It's okay. So, from a 0, 1 state, and a 0, 1 state, if I go to 0, 0, whatever output was there originally, that is retained. Is it alright? Okay. Now, originally, I put a 0 here and a 1 here. A 0 here and a 1 here. Since this is 0 and 1, I got a 1 here and a 0 here. That is clear? At that time, I don't do any change here. That is written at 0. This fellow, I go take it back to 0. If I take it back to 0, before that, this was in one state. See here, that is 1. This is in one state. This was in one state. Both the inputs to OR gate are 1. I make this 0. OR gate does not care. As far as the OR gate is concerned, if any one of the inputs is 1, OR gate output is 1. If any one of the inputs is 1, NOR gate output is 0. So even if I take this back to 0, this gate is not going to change state. Output will continue to be 0. If that is going to be in 0, both these are 0, 0, this output will be 1. Is it alright? Clear? Is it clear? Is it clear? So all the trouble I am taking, what I am telling you is, the old state is retained. For the first time, we have woken up to the fact that something was happening earlier, when some change has occurred, something else has not changed at all. The previous state is retained, just in the binary form. There is a 1 earlier, that is retained as 1. There is a 0 earlier, that is retained as a 0. The last state is retained here. So when you go back from 0, 1 to 0, 1 to 0, 0, that state is retained. From 1, 0 to 0, 0, this state is retained. It's okay? It's alright? That's a basic property of this circuit element that we have got. First time we have built up a circuit element where something which was available in the past instant of time has been carried over. In fact, that next state is not used at all. So we can as well ignore that. In fact, the subsequent operations are all done such that that next state will be avoided, because that gives a problem that is avoided. So I would like to encash, see, my job is not to see in what all ways I can use. My job is to see in what all useful ways I can use the gates. The useful way I can use the two gates is to have the memory property. To have the memory property, the simplest way of doing it is use two gates. Use two NOR gates, connect them in this crisscross fashion. The simplest NOR gate connection where one binary bit value is retained. Now this is the basic circuit for us to build up whatever we want to do maybe for the next 2 hours.
0, 0, what was there?
It will be there. What was the previous value? If you give 0, 1, if you give 0, 1, that's a unique output. If I give 0, 1 as input, Q will go 1. If you give 1, 0, Q will go to 0, that is unique. But if you make both of them 0, 0,
Whatever is the previous state,
that is retained. That is retained. It is not unique. Do you understand? If it is 0, 0, output can be 1, 0 or 0, 1. Output can be one combination, or take only Q value. Don't bother about Q bar. Q bar is an inversion. Forget about Q bar. We'll take only Q. That Q, if I take 0, 0, Q can be 1 or 0. Both are possible. How do you decide? That is decided by the past, the latest sin that you committed. That will decide the Q value. Okay? It's alright? You understand how memory is built up. Just only this particular simple principle. You have one that was available, under some conditions it is retained. We'll simply exploit and encash on this. It's okay? It's alright? It's okay? I just explained this in detail here. Whatever I told earlier is put in words here, that's all. A flip-flop can be in reset state, it can be in set state, but the moment R and S, both of them go to 0, the old state continues. The sin is retained. The last state is prohibited, we will not look at that. Every one of the subsequent things that we deal with, it can be a flip-flop, it can be a counter, register, etc., all these cash in on the memory property. Now, incidentally, I can build flip-flops with the other universal gates. All of them will function in a similar fashion. Two NAND gates, two, gates with this bubbles at the input side or bubbles at input side here. Every one of them will function the same fashion. Only slight differences in the R is 1 or S is 0, etc. That combination only will change. Otherwise, the functioning is similar. Initially, you can just reflect upon this and see how they function and what ways they are different from the basic flip-flop that we discussed earlier. Okay, I added to the confusion here. I have done something more here. I told you I would like to exploit the flip-flop as much as possible. I have done here, I have taken the basic flip-flop. I have done the basic flip-flop I have taken. I just added 2 AND gates here. I put a common input, which I call as an enable input. You understand? I have taken a common enable input for both of them. If the enable input is 0, nothing will go through. If the enable input is 0, this will be 0, this will be 0. The old state will be retained. If the enable input is 1, at that time only, any change in R and S will be taken cognizance of by the flip-flop. So if the enable input is 0, the flip-flop condition is set, it is retained frozen. It is in memory state. Flip-flop is not accessible to the S and R. Nothing can be done. Only when this enabled fellow goes high, S and R can do something. The enabled fellow is like a peon in a government office. If that fellow sleeps and he says nothing, no entry. Only if you satisfy him, anything can happen inside. That is what the enabled fellow does. Okay? Enable is 1 means you have flip-flop behaves as an RS flip-flop, what we discussed earlier. If it is 0, it is frozen. If it goes, the moment you take it high, you take enable high, you do with R and S whatever you want, you take enable low, the flip-flop has captured the last state of R and S. The flip-flop has captured, it is retained. It is alright? It's okay? I have shown set of operating waveform here. See here? I have shown, see enable is, wherever enable is 0, R is changing, S is changing, output does not change. Flip-flop does nothing here. Here again, enable is 0, it does nothing. But when it goes high, whatever is it, see R is high here, S is low here, flip-flop is at 0 state. When it goes high next time, both are 0, 0, old value is retained. When it goes high next time, S is high, output goes high. See here, the output has changed high here. Next time, when it goes high, R is high, S is low, so it is reset. So the flip-flop output changes only when, En goes high. At that time, whatever the value of R and S, it is sensed and frozen. R and S values are sensed when En goes high, and they are kept frozen. That is the storage here. So I added to a facility substantially by putting an En. Now, to make it more precise, normally what is done is that FF signal, that En signal, you make it just very, very sharp. Then it is called an edge-triggered flip-flop. You make it positive edge or a negative edge. So only when that star pulse is coming, the flip-flop will operate. Rest of the time, it will keep quiet. It's called an edge-triggered flip-flop. It's okay? It's more often then identified as a positive edge-triggered flip-flop or a negative edge-triggered flip-flop. Number 1. Second thing is, whenever you are putting an edge-triggered flip-flop, that En signal will be called a clock signal. That is at regular intervals. I just see what is the S and R and I just do an operation. It is a clock signal. The clock signal, it is kept as a periodic signal. I am just slowly building up what is required for a processor. So I have an enabled signal, I make it an edge-triggered operation, I make that enabled signal as a periodic waveform. It is a regularly operated clock. That is at time t equal to 0, I do an addition. Time t equal to 0 and t equal to 1, I do a logic operation. etc., etc. Or I want to add 10 numbers. Time t equal to 0, add number 1 and number 2. Time t equal to 1, add number 3 to it. Time t equal to 2, add number 4 to it. You go on doing that. So at every time instant, you do the first operation, second operation, third operation like that. You just, it is like, that NCC marching. One whistle, do something. Next whistle, do something. Do your whistling at regular intervals. Do in a well-ordered fashion. Everything goes off smoothly. Okay, I have shown the same thing. I have shown it as an S trigger flip-flop. This is the symbol that is used. You got an S signal, R signal. The enabled signal is put like this, means it is positive S triggered. Your output takes new state at the positive edge of En. Yeah. You are reducing the speed. I'll come to that. Or sometime I'll come to that. I'm coming. I'll proceed. This is the other case. It's a negative edge trigger flip-flop. This is a symbol. You put a bubble here. It is a negative edge trigger flip-flop. All the operations are taking place at the negative edge of En. At this edge, what is the value of R and S? That decides the output. Here, R and S, that decides the output, and so on. After that, it remains frozen. Earlier it's a positive edge trigger, here it's a negative edge trigger flip-flop. In all digital systems, it is customary to work with either only positive edge trigger flip-flops or negative edge trigger flip-flops. More often, we work with negative edge trigger flip-flops. So wherever it is not mentioned, I'll take it as negative edge trigger. The operation is similar. Whether one or other type, operation is similar. Now, Sumar was asking, what is the use of all this? It's putting your clock. Now, when I put a clock, when I put an EN signal as a clock, and I say that the operation is taking place at 0th second, first second, second one, third second, fourth second, etc. Mine is a timed operation. I know the operation is going to take place at fixed instants of time. Okay, that is called a synchronous system. In a synchronous system, the whole set of operations are decided by the basic clock, the clock rate. The clock rate may be 1 megahertz. The clock rate is 1 megahertz. An operation will take place at 0th microsecond, first microsecond, second microsecond, third microsecond, etc. That is a characteristic of a synchronous digital system. Now, if you don't do that enabled clock input, you work with only logic gates, then also you can do multiplication, summation, division, whatever you want to do, you can do. That is called an asynchronous system. There is no clock involved. You give your inputs, you get your outputs. You do a memory, you give another signal, that goes to storage. Take a signal, get output. You can do. That's called an asynchronous system. When you do a synchronous system, number one, there is a predictability. I know that things are going to take place at this instance of time. Throughout my digital system, everywhere, whatever I arrange, I can arrange so that the things take place at that predetermined instant of time. That's an advantage of a synchronous system. Apparently, I am losing out on something. Sorry. I am not able to cash in on the speed of the system. I give a set of logic inputs, output has taken new values, I have to wait for the next clock input to come and then take the new value. Apparently there's a slowing down. But that is not right. It is something like this. If you take that multiplier that we discussed earlier, if I take a 8-bit by 8-bit multiplier, by the time that signal goes through and you get the output, it may cause a lot of delay. You don't know that the delay is 1 microsecond or 100 microseconds. There's no precise way of knowing whether the delay is so much, it can be accommodated, it cannot be accommodated. Whereas here, there's a high level of determinism that you have introduced. So wherever possible, we work with a synchronous digital system. We don't work with an asynchronous digital system. As the system size increases, definitely work with only a synchronous digital system. With asynchronous digital system, that indecision can create a lot of problem because you, as you increase the size, you don't know whether you have got a proper output at this time, etc., etc. You would like to rather, suppose I know I work with a system, with a clock at 1 microsecond. With a clock at 1 microsecond period. I know whatever I am going to do is going to take place at 0th microsecond, 1st microsecond, 2nd microsecond, 3rd microsecond, 4th and so on. I know this is going to happen. With a synchronous system, that is okay. If I work with a corresponding asynchronous system, suppose I got a circuit. I got a circuit where the time delay for operation is say 0.9 microseconds. I give two inputs, I expect an output here. The delay can be anything from 0 to 0.9 microseconds. I put this circuit here and work with that. I know that the maximum delay is 0.9 microseconds. So at the 0th microsecond, if the inputs are come, output would have come at the 0.9, first case, 0.9 microsecond. Before the next clock pulse comes, the new values have come into picture. Is all right? But in an asynchronous system, when I work with this, so far so good. But suppose I put two of them here, and I take the output. In an asynchronous system, I have to go for a delay, I have to wait for 2 microseconds to operate. In a synchronous system, I will not do this. In a synchronous system, I will not do this. I will take this output, use this at 1 microsecond, refresh that, take this only at the 2nd microsecond. Do you understand the trouble I am taking? You just imagine 100 circuits like this. You imagine working with 100 circuits like this. Wherever you are certain that your delay is less than your clock period, you simply work with a synchronous system. If you are not sure, God save you. So that's why we go for a synchronous system. I don't know if I made the point clear. Have I made the point clear? You ensure that at every block, the maximum delay that can come into picture is less than the clock period. The moment you have ensured that, a synchronous system you can just run riot. You can put as many circuits as you want. In the asynchronous case, you are never sure whether it is 1 microsecond, 100 microseconds. Is it all right? So wherever your system is very small in size, you can afford to go in for an asynchronous system and cash in on that so-called improvement in speed. As the system size increases, you cannot do that. So wherever possible, as the system size increases, you go for a synchronous system. It's okay? So the advantages are, it is fully predictable, the indecision is low here, a synchronous system is always preferred. The basis of the synchronous system is the X-trigger flip-flop. Now, I am taking one step further. The same S-trigger flip-flop, instead of giving two inputs, I have taken the same input here, put an inverter and given here. So S input, R input is just an inverter. It is called a D flip-flop. You can call this a delay flip-flop or a data flip-flop. It is a D flip-flop. This is a symbol used. One time delay. Okay. Basically, a D latch has two broad functions. One is a function when it is asleep. When a D latch is asleep, it retains the old state. Input may change, it may go haywire, 0, 1, S and R values, they may go 1 state, 0 state, whatever is that, D latch is asleep. It has retained the old value. The second state is the D latch is awake. If S is 1, R is 0, it replaces that value. If S is 0, R is 1, it replaces that value. And so on it goes. That is the second state of the D latch. So, in one case, the D latch is transparent. See here, whatever D is there, that is repeated as Q. The D latch is transparent. It is innocent. It does nothing. No corruption. Whatever input data is given at the D line, it appears at Q as soon as enable is high. In this case, it says nothing doing. I return the last value and that will remain. Is alright? That's a D latch. Now this is one step ahead. An edge-triggered D latch. An edge-triggered D latch, it will just sense the value of D at that edge, at that negative edge, and then it decides what will be the output. That's all. Again wait for the next clock, next negative edge, sense the D value, retain that. Again go back to sleep. On and on. At every negative clock edge, what will be the value of D, that will be sensed, it will be frozen and retained until the next clock edge. You see here. This is the EN value. It has sensed it here. D is high. I don't know where it has sensed. Okay. I'm sorry, it's a positive edge triggered flip-flop, hopefully. So at this positive edge, the D value is 0. It senses and retains as Q. Thereafter D is changing. It is going here, up, down, up, down. D is trying its best to change. The flip-flop says, no, I will not take this. I will remain at this value. Again, the next positive edge on E. At that time, again it senses the value of D. D is 1. It takes the value. The new value is retained until, once again, the E goes as a positive edge. Is alright? That is an edge triggered flip-flop. Edge triggered D flip-flop. One is a D latch, the other is an edge triggered D flip-flop. We will use both of these in our circuits. In many cases you will find that when you work with the flip-flop, when you switch off the flip-flop and switch on, there can be an indecision. You don't know what state it will go in. To take care of that, your flip-flop will have additional inputs. These are called the clear and preset inputs. This will also be added to flip-flops. Normally they are called clear input and preset inputs. They will be added to the flip-flop side separately and independent of the external enabled clock. So using this clear and preset input separately, I just give this, I put on the power. If I want to go the flip-flop to be taken to state 1, I make this signal high. This will go to state 1. If I want to just make it 0, I enable this signal. So using these two, I can set the value of the flip-flop at the starting time. So they are called the preset and clear inputs. They are given independent of these two. Your data and clock, independent of this, that will be given separately. All these are available in the flip-flops that we work with. How long do you think we can continue? You stop or another 10 minutes? No? It's okay. It's alright? A JK flip-flop is built around an RS flip-flop with 2 additional gates. Now, in the next few slides, I have shown the logic of working of a JK flip-flop. I will not go into the details. I will do as we do typically in some of the classes. Like, the last few days, you say that I have to do a lot of things. So I'll just leave it to you. I'll just give only the end result. I'm not sure what I'm going to do, or I'm not sure of the topic. So you leave to the students to study. I'm doing a similar thing here. I think we will not go into the details of working on the JK flip-flop. You go through carefully the logic. I think you'll understand. If there's anything to discuss, you please tell me. We'll discuss that separately. I'll just give the end result. So you just go through carefully, you can understand the working. I have given here the truth table of working of the JK flip-flop. First of all, the JK flip-flop will do anything, if at all, only when the clock pulse comes in. At the positive pulse of the clock, only when the positive pulse comes here, there is any change in the JK flip-flop. If there is no pulse, there is no change, no activity, the morosity continues. Only at the time of pulse, any change will come into picture. So all the discussion I do is concerning the coming into picture of a pulse and the clock inputs. I given the truth table I given here, what will happen when a pulse comes into picture. If the J and K values are 0, if J is 0, K is 0, if J is 0, K is 0, it will retain the old state. The flip-flop will retain the old state. If J is 1, K is 1, the flip-flop will go to one state, just like RS flip-flop. If J is 0 and K is 1, it will go into the reset state, just like the RS flip-flop. Okay? These three are clear. Here, old values retained. Here, the set or reset state is decided by the combination of J and K. Now, I come to another state here. If J and K both are 1, if J and K both are 1, the flip-flop will flip. Whatever original state it had, it will simply change. If it was in one state, it will go to 0 state. If it was in 0 state, it will go to one state. That is called a toggle. It's called a toggling of the flip-flop. Just it will swap whatever original state it had, it will do a swapping of that. So that's a new state that we added, a new dimensional working of the flip-flop. Now we will see how to make use of the flip-flop, JK flip-flop, for various operations. So I got here 3 modes of operation for the JK flip-flop. In one mode, the old value is retained. In another mode, the present state is decided by exclusively the J and K values, whether it is 1, 0 or 0, 1. In the third mode, where J and K both are 1, the flip-flop will just change its state. There are 3 modes of working of the JK flip-flop. In many of the digital systems, the basic flip-flop that we work with is the JK flip-flop. Normally, you can add a clear and preset signal to the JK flip-flop so that at the time of starting off, we can wash all the passes in. You can make the flip-flop go to one state or 0 state as you desire. And then you work from there. There's no illegal state here. Every state is predefined and just deterministic. Now, just like a JK flip-flop, there is another flip-flop which is called a master-slave flip-flop. Functionally, that's also similar to JK flip-flop. Every state is well-defined. It works in a well-defined manner. Digital systems, complete systems are built up using master-slave flip-flop. Normally, you can have a JK flip-flop to build a digital system or a master-slave flip-flop to build a digital system. Either one or the other is commonly used. I will not go into the details of this because for our purposes, one type is enough. Now, I'll take up counter as an application. Do you think I'll do one counter and stop, or we'll do in the afternoon? What are you saying? We'll stop? Stop. Saturation. What time do you meet? 2 o'clock? 2 o'clock is okay? We'll start off with counter. Today we'll do counter. We'll complete this chapter. Maybe it will take another hour. Counters and registers. That will maybe go up to about 3 o'clock.